Welcome back. In this series, I have shown that solar systems are quantized exactly like atoms, and that the positions of planets in a solar system are in integer multiples of the fundamental radius. This is the same for the orbits of electrons. However, people argue that, for solar systems, we can have many other orbits in between two consecutive orbits, such as orbits of satellites, and go further to claim that this is not true for atoms. That there cannot exist orbit between any two orbits of an atom. This is what I seek to clarify in this video, and I shall achieve this exclusively by analyzing data from many different solar systems. My hypothesis is as follows. For any set of bodies in a solar system massive enough to be called planets, the orbital radius of each planet is an integer multiple of the radius of the first planet, which is also the smallest possible or allowed radius. Mathematically, we write Rn equal to nr0, where r0 is the first radius, Rn the general radius of any planet, and n running from 1 to infinity. This means that for a solar system with n number of planets, if we measure their respective orbital radii and plot it against n, we will have a straight line. So what we need to do now is go out and look for other solar systems and measure the radii of their planets. Fortunately, such data already exists, so let's use it to test my hypothesis. Before we continue, please take a second to click on that subscribe button to support this channel, and the like button to enable the YouTube algorithm to promote this video. Let's take for example the solar system Gliese 876, which has 4 known planets with orbital radii as follows. The first radius is R0 equal to 0.0218 astronomical units. So for values of n from 1 to infinity, the allowed values of radius Rn are as follows. When we plot Rn against n, we have the following perfect straight line graph. Now let's check if this is consistent with the already measured radii of the other planets. The second known planet has orbital radius 0.136 astronomical units, and that should be somewhere around here. When we extrapolate down to the n-axis, we see that it falls close to n equal to 6. The next is 0.2186, and extrapolating in the same way leaves it near n equal to 10. And the next, which is 0.35, falls near n equal to 16. Let's take these n values to be the n values of the planets. You can call it the quantum numbers if you like. This yields the following data table of Rn and n. When we plot this is what we have. Therefore, the best trend line is like so. The slope of this graph is equal to R0, and I think this will yield a better value for the first radius. So, not only does this data analysis confirm my hypothesis, it also provides a means to predict all possible orbits where one can expect to find a planet in a given solar system. Any other object out of these designated spaces must therefore be a satellite. Well, you may be saying at this point that that is just one solar system, but I would like to assure you that this works for all solar systems. I have generated the graphs for more than 40 solar systems so far, so let's quickly go over a few more. Let's take the solar system 82G Eridani with planetary radii as follows. Here, R0 is equal to 0.095 astronomical units. Hence, Rn is as follows. This plot gives the following perfect straight line. The actual radii are at the following positions. Now, let's make our table of data. Planet 1 has n equal to 1. Look at planet 2. The n value is still close to 1, so this cannot be a planet, but rather a satellite of planet 1. So we insert a dash. The next planet falls close to n equal to 2, the next close to n equal to 4, and the next near n equal to 5. Now, if we plot this data, we obtain the following graph, which is still a good straight line. The yellow dot is the plot of the satellite, so my hypothesis also holds here. Take the next solar system, Tau Ceti, with planetary radii as follows. By the same approach, we obtain the following perfect straight line. The mapping of the actual radii are as follows. To save time, let's make the other plot on the same graph. Approximating to the nearest quantum number, we obtain these points. Again, the ones in yellow show that those alleged planets are actually satellites. From these points, once again, we can obtain a very good straight line. What about our solar system? These are the orbital radii. The first orbit is this, so we have the following plot. For the actual radii, we have the following extrapolations that yield the following quantum numbers for the planets. The plot of the actual radii against the quantum numbers yields the following graph. The slope of this graph is equal to 5.1 exponential 10 meters, and this is what I took as my R0 in my other videos and used it to calculate my universal Planck's constant G. If you have the time, you can do this procedure with any solar system and confirm that my hypothesis is correct. From these results, I can thus conclude the following. 1. That the formula R equal to nR0 is correct for all planets of a solar system. 2. That there can exist other masses or bodies in other closed orbits, but bodies are not planets. In my analysis of solar systems and atoms, I likened electrons to planets. Let's have a quick recap on why this was so. By using purely circular motion, I derived the expression for the angular momentum of an electron as follows, and for planets as follows. I have made these derivations many times in many of the previous videos. You can refer to this one or this one for the derivations. At this point, I needed to invoke the quantization of orbital radius. Niels Bohr used R equal to n squared R0. Subbing this in the momentum of the electron yields n times the square root over 2 pi. Many times we have confirmed that subbing in the values of the constants under the square root yields 6.4 exponential minus 34 joules per second, which is the value of the Planck's constant h. So equating this square root to h leaves the momentum equal to nh over 2 pi, the famous Bohr quantization formula where atomic number is equal to 1. If we did the same for solar systems, we will obtain L equal to ng on 2 pi, the same kind of formula with g equal to this square root. If you are a critical thinker, click on that subscribe button and share your thoughts in the comments section below. Don't also forget to like the video to support this channel. We have seen from our solar system analysis that R equal to n squared R0 is not the appropriate formula, but rather R equal to nR0. If we use these instead, the momentum equations take a square root on n, and are as follows. I showed in the video titled, What if solar systems have electronic configurations, and in this other video, that writing the momentum this way with the square root can explain perfectly electronic configurations of all atoms without the need for the 4 quantum numbers. It was also in perfect agreement with the fine structure splitting observations and the Zeeman effects. So, beyond any reasonable doubt, I proved that the angular momentum of an electron is equal to the square root of n times h over 2 pi, not nh over 2 pi. Today, we have also seen the proof that r is equal to n r0 for solar systems, which leaves the momentum equation of planets as L equal to square root of n times g over 2 pi. This confirms that, truly, planets are electrons of atoms. By this argument, since there can exist satellites in solar systems, there can also be satellites in atoms. These atomic satellites must be equal to or less than the size of the electron, and I can think of many particles that particle physicists have discovered that meet these criteria. So the fact that electrons exist in discrete orbits does not necessarily mean that other atomic particles cannot exist in orbit in between, as we have seen in our solar systems. So those of you that were using this as your argument against why solar systems and atoms are not equivalent will have to rethink. Be sure to subscribe for more clarification, and you can also drop your comments and I will clarify you. Stay tuned and thanks for watching.